All right, well, we're going to move into a new topic today. And normally this is the topic I do at the end of the term, but I want to make sure we have enough time to get through this because I think it's one of the more interesting topics. And I've been told by students who have gone on to WSV, for example, that this section of the course was really helpful to them, that it helped them when they took automata theory elsewhere. So I want to make sure we have time to get through this. I've posted your next homework for this unit. So we're doing languages and automata theory. And this will be about a week. And then the last week we'll probably come back and pick up some graph theory. So homework is posted. If you're walking in late, go ahead and drop off your homework if you have it. So we're going to talk about languages and grammars. And our goal here is basically to look at different ways that we can define a language or a grammar. Ways that we can answer questions like, how do we structure a sentence in a particular language? How do we look at a sentence and know if it's valid or not? And there's going to be an important distinction in what we do, which is the distinction between syntax and semantics. And we're strictly going to be looking at syntax. We're not going to worry about semantics. So semantics refers to the meaning of something. Syntax is the structure of something. So for example, in C, we have a very rigidly defined syntax. If you have this kind of statement, you have to have a semicolon at the end. If you have a function call, you've got to have parentheses with 0 or more arguments separated by commas. That's all syntax. There's really no restriction on the semantics of a C program, though. So we can write a C program like this. And is that a valid C program? Absolutely. It will compile, it will link, it will execute. But it doesn't do anything reasonable, right? The semantics of this is just totally ridiculous, right? We have an if statement that will never fire. We have an else statement that just sets I to 0. And if that if statement did fire, it would do exactly the same thing. And then we don't even do anything with I. Syntactically, it's perfectly fine. Semantically, it's gibberish. Okay, we don't care about semantics for what we're discussing here. We're only looking at syntax. So for us, we would analyze this and we would say, yes, that is a valid C program. So Noam Chomsky studied languages extensively, and there's aspects of this theory that are named after him, Chomsky hierarchies and so on. And he would talk about things like the sleeping, colorless green gas eats hungrily, right? And it's a perfectly fine syntax, but it's a stupid statement, right? Because you can't be colorless and green at the same time, and gases don't sleep, and gases don't eat, et cetera, et cetera. Okay, so we're looking at syntax. And so we want to think about formal languages. Which means that English is probably not something we're going to spend a lot of time thinking about, because English is not a very formal language. The rules of English are just insane, right? If you learned English when you were very young, you sort of took these things as a given. But if you think about them as an adult, they're kind of random and ridiculous, right? Which is why English is such a weird language to try to learn. There's not really a rigidly defined set of rules. There's always these exceptions and so on. So we want to sort of go to the other extreme. We want to look at very formal languages. But we'll pick on English as a language we're familiar with, and we can try to make at least some piece of it formal. So here's an example of how we could define an English sentence. So we could say a sentence is the following. It's a noun phrase plus a verb phrase. And this obviously doesn't work for all sentences, but we can define a sentence to be a noun phrase followed by a verb phrase. And we can define a noun phrase to be one of the following. It could be an article plus an adjective plus a noun. Or it could just be an article followed by a noun without an adjective. And a verb phrase will be a verb followed by an adverb, or it may just be a verb. This is recursive, right? I haven't told you anything usable yet, unless I tell you what an article is and an adjective and a noun and so on, base cases. So our base cases are the following. An article is either a or the. An adjective is either large or hungry. A noun is a rabbit or a teacher. A verb is hops or speaks. And an adverb is quickly or happily. And now we have enough to create sentences and to identify something as a sentence. So we can use these definitions, and for example, we can create a sentence. How would we create a sentence? Well, we need a noun phrase, and a noun phrase could be an article, adjective, noun, or an article, noun. Let's do an article, noun. So article will be the, and let's say noun is a rabbit. So that's a noun phrase, and then we need a verb phrase. So let's do a verb and an adverb. Let's say speaks, and our adverb will be quickly. So that's a valid sentence according to this structure. The rabbit speaks quickly. Okay, you ever play Mad Libs? That's all we're doing here. So Mad Libs are things like this, but they leave these terminals, adjectives, nouns, verbs, blank. And you ask someone to give you a noun, give me an article, give me an adjective, you write them in, and then you read the sentences, and they come out funny. All right, we can also identify something as being a sentence. So we could take a sentence like, the hungry teacher hops quickly. And we can say, is this a sentence? Well, if it's going to be a sentence, there has to be a noun phrase followed by a verb phrase. And through some trial and error, we could eventually discover that this is probably a noun phrase, and this is probably a verb phrase. How do we know that? Because this is an article, and this is an adjective, and this is a noun. And an article, adjective, noun gives us a noun phrase, and this is a verb, and this is an adverb. And a verb adverb gives us a noun phrase, and a noun phrase plus a verb phrase gives us a sentence. So we can work down to confirm that something's a sentence, or we can work from the bottom up and construct sentences. And that's pretty typical. Well, we want a way to make this more formal. okay, to be able to do this without having to go through this sentence diagramming Mad Lib kind of exercise. So we're going to define a grammar, and a grammar is going to be a very formal way of describing what's valid inside, what sorts of sentences are actually valid. So we need some definitions. So a vocabulary V is a finite, non-empty set of symbols so we have to define what the symbols are. Think letters, if you like, for English. A word, or sometimes a sentence, over that vocabulary. So a word over V or a sentence over V is a finite length string of elements of V. So V is our vocabulary. It's a collection of symbols. A sentence over V is just a finite length string of symbols from that vocabulary. You could have repeats. That's fine. And you could also have a word or a sentence of 0 length. So lambda equals the empty string. So it's a word or sentence of no length, so containing no symbols. And this is not the same as the empty set. Right? The empty set is a set, a collection of elements containing no elements. Okay? Lambda is a string, so a string is an ordered arrangement of symbols from our vocabulary. Okay, the order is important, and our string could have no symbols in it. It could be an empty string. But don't think of it as a set per se. All right, so V with an asterisk on top. This is the set of all words over V. So let's keep some examples on the side while we're doing this. So example, our vocabulary might be just the two characters 0 and 1. Okay, those are our only symbols. And so some words would be 0, 1, 0, 0, 1, 0, 0, 1, as well as the empty string. And V star would be the set of all possible words. So it could be the empty string, it could be 0, 1, 0, 0, 0, 1, 1, 0, 1, 1. And so on. And that's clearly an infinite set. So all the possible words you can make over that vocabulary. So what we're after is a language. So a language over V is a subset of V star. So we're looking for a particular collection of strings that are interesting to us. That's what we're going to call a language. So in the case of English, our vocabulary might be the set of all letters. and a word over that vocabulary would be a finite length string of letters, and V star would be all the possible combinations of letters that you can make as long as it's only a finite length collection. And then the language would be the particular subset of letters that you find in the dictionary, right? The ones that we consider to be part of the language. In the case of our vocabulary of zeros and ones, our language might be all the 8-bit strings with an even number of zeros, or whatever. So how do we specify a language? And there's a few options here. One option is to list all the valid words. Just make a list of every word that's valid over this language, every word that's a piece of this language. And we do this in English. That's exactly what a dictionary is. It's quite literally a list of all the words that are valid in English. Right? The bigger the dictionary, the more comprehensive. So that's one option, but that's not a very usable option. You wouldn't want to write a C compiler that stores every possible C program in a file and compares your file to every possible one to see if it's valid, right? So that's not a very practical approach. A second option is to list rules for a word to be valid. I before E except after C. Q is always followed by U. Have to have at least one vowel unless it's syzygy, and so on and so forth. So we do that in English also, right? And that sometimes works, but sometimes it usually works, but not always. And that doesn't work well for C either. So the approach we're going to be most interested in is describe a grammar. For the language. And a grammar is basically some symbols and what we call rules of production, rules for creating words. Which we call production rules. Sort of. This is really saying how can we look at a word and tell if it's valid. This is saying how can we create a word. So you can start with any letter you want. If it's a Q, it has to be followed by a U. Otherwise, it can be followed by anything. When you get to the end, there has to be a vowel somewhere, and so on and so forth. If you have a T followed by an H, etc. They're similar, but we're really interested in creating words using this grammar. So a phrase structure grammar So it's a four-tuple. It's a vocabulary, a list of what we call terminal symbols, T, a particular start symbol, which we call S, and a set of production rules. Okay, V equals vocabulary. T equals set of terminal symbols. S equals the start symbol. And equals a set of productions. So how does this work? Let's do an example. So here's our grammar. It's a 4-tuple. Our vocabulary consists of the following: little a, little b, big A, big B, and S. Our terminal symbols are just little a and little b. Our start symbol S is just this little s. And our production rules are the following. So S can be replaced with big A, big B, little a. Big A can be replaced with big B followed by big B. Big B can be replaced with little a, little b. And big A, big B can be replaced with little b. So we have 4 elements in our set of productions. So what these productions mean is that if we have an S, we can replace it with big A, big B, little a. If we have a big A, we could replace it with a BB. And if we have a big B, we could replace it with a, little b. And our terminal symbols won't appear on the left side of these production rules. So if we have a little a, it's just going to be a little a. And this big B could be replaced with a little b. And this could be replaced with a little b. And this is still AB, and this is A. So from S, we can get to the following string, AB, AB, ABA, which means this is a part of our language. So anytime we can start with the start symbol, apply our production rules, and come up with a string made up of terminal symbols, that string is part of our language. So is there anything else in our language besides this string? Yeah, so S can be replaced with A, B, A. But we have a rule that says big A, big B can be replaced with little b. And so BA is also a part of our language. But it turns out those are the only 2 strings in this particular language. Okay, but this is a general methodology by which we can specify more or less arbitrary languages.
So is there always only one starting variable?
There's one starting symbol S, yeah. I think you could probably do this with more than one, but I think you could change it into, right, if you wanted 2 start symbols, you could have one start symbol and transform that into either of your 2 starting symbols, and then you're good to go. All right, so we need some more definitions. So suppose we have some word W0, and it's equal to something on the left, followed by some middle part Z0, followed by something on the right. And suppose we have another word, W1, which is the same stuff on the left, followed by some different middle part, Z1, followed by the same stuff on the right. So if we have a production rule for changing Z0 to Z1, so if that rule is part of our production set, then we can say W1 is directly derivable from W0. Right, in the sense that we can use this production rule, change that middle Z0 to Z1, and we've got W1. And we can write this as W0 and a double arrow, W1. And it's nothing to do with propositional logic, right? It's just reusing the double arrow to mean something totally different. So this means W1 is directly derivable from W0. Now, if W1 is directly derivable from W0, and also W2 is directly derivable from W1, and W3 from W2, and so on, until we get to Wn. This means there's a production rule that will change W0 to W1. This means there's a production rule that will then change W1 to W2. So a combination of production rules will therefore change W0 to W2, and so on. And so we can show that if we have W0 and all of these things are directly derivable, we can eventually get to Wn starting with W0. We just change it into W1, 2, 3, and so on, n minus 1 times. So in this case, we say Wn is derivable from W0, but not directly derivable if we have to use more than one production rule. But it is derivable, and we can write this as W0 gives us Wn, but we put a little star on top of the arrow. That means derivable, but not necessarily directly derivable. So over here, we could say that ABA will let us eventually get to AB, AB, ABA. But we could also say ABA will get us directly to BA. All right, so here's our final definition. The language generated by G generated by a grammar G we can write this as L of G, and this is the set of all strings of terminals which are derivable from S. which we can make totally mathy by saying it's a set of all words in T star, right? All combinations of all strings containing characters of our terminal symbols. A set of all W in T star such that W is derivable from S. So everything we do, there's going to be sort of two versions of our problems. One is analysis, the other is synthesis. Analysis is usually easier. Looking at something and saying, is this, what's derivable from this particular grammar, right? What are the things over here? That's an analysis question. That's going to be fairly straightforward, and we'll start off with that. But then we're going to move to synthesis, which is, how can we construct a grammar which corresponds to this particular set of words? Can we make a grammar for a string of 0 and 1s that has the same number of 0s and 1s? Or has an even number of 0s followed by an odd number of 1s? Or things like that. So let's start with some analysis. And I'm not going to keep writing G of V, comma T, comma S, comma P. Okay, we'll just stick to those. V is vocabulary, T is your terminal symbols, S is your start symbol, P is your set of production rules. Okay, and let's just look at some examples. So for example, your vocabulary might consist of a start symbol, A, little b. Your terminal symbols will usually stick to just lowercase letters for our terminals, just to make it easier. Our start symbol is pretty much always going to be little s, so we don't have to worry about that. So it's mostly going to be a question of what's in our vocabulary and what are our production rules. So our production rules for this case are the following. S can go to little a followed by big A. S can go to B, little b. And big A can go to two little a's. So what is the language over this grammar? Language generated by this grammar. So what are some words we can get?
B.
We can definitely get B because our start symbol S goes directly to a B. And we can get, you can get AAA, right? So S can go to little a followed by big A, and big A goes to two A's. So S will go to three A's. And that's all we're going to get. So again, this is a simple grammar. It's only got two things that it generates.
So a language is like, no. So is the language a set? Is it a set containing strings?
Mm-hmm.
Okay.
Yeah. The language is a collection of words.
So like technically you could use the language as a vocabulary to make set sentences or something?
So word and sentence are the same thing. We use them interchangeably.
Yeah. Well, I'm thinking if you made a set of words, you could plug that into a different function to make another language.
Sure. Yeah, yeah. All right, let's look at a more interesting example. So our vocabulary is S, 0, and 1. Terminal symbols are 0 and 1. Start symbol is S, and our production rules are the following. S can go to a 1 followed by a 1 followed by an S, or S can go to a 0. So let's find some things that are specified by this language, specified by this grammar. So what's something we can get from S? We can certainly get to 0, so that's one word generated by this grammar. What else? So S could take us to a 1, 1 followed by an S, and S is a 0. So this is also part of our language. What's another word? And you can see where this is going. So our language has an infinite number of words in it, which is kind of cool because this was not an infinitely long definition, but it's got an unlimited number of words. And the general makeup of our language is any string containing an even number of ones followed by a 0. And that's a nice, succinct way to capture that language. All right, let's try another. So our vocabulary is 0, 1, A, B, and S. Our terminals are 0, 1. Our start symbol is S. And our production rules are as follows. So S can change into 0A. S can change into 1A. A can change into 0B. B can change into 1A, and B can change into 1. So let's explore this. So what kinds of things are in this language? So S is our start symbol. And this is where doing something tree-like can help. So we know that everything has to be derivable from S. And S could be 0 followed by a big A, could be 1 followed by big A, and that's it. So we know our string is going to start with a 0 or a 1. A big A could be a 0 followed by a B, and that's the only thing that a big A can change into. So this is a 0 followed by a B. But a B, we have two possibilities. B could be a 1, or it could be a 1 followed by an A. And an A, again, is a 0 followed by a B. And a B is a 1, or it's a 1 followed by an A. And so pretty clearly, this can go on indefinitely. We can get an infinite number of strings of any length. But let's look at some of these cases where this tree terminates, where it has a leaf, right? Because this can keep going. So it could be a 0 followed by an A, which is a 0, followed by a B, which is a 1. Or it could be a 1 followed by an A, which is a 0, followed by a B, which is a 1. Or it could be a 0 followed by a 0, followed by a B, which might be a 1, followed by a 0, followed by a 1. Or it might be a 1 followed by a 0, followed by a 1, followed by a 0, followed by a 1. So is there a pattern here?
Words are not number of digits. The first digit can be 0, but every pair of digits after that is 0.
Right. So it's going to start with a 0 or a 1. So this is a set of strings starting with 0 or 1, followed by, well, it's followed by an A. And what is an A? It's either a 0 followed by a B, which is just a 1, or it's a 0, 1 followed by another A. So when analyzing these, sometimes it's helpful, instead of just trying to figure out what an S is, figure out what an A is, right? An A is either 0, 1 or 0, 1 followed by an A. So it's followed by one or more occurrences of 0, 1. So it's 0, 0, 0, 1, 0, 0, 1, 0, 1. Or same thing starting with a 1. Make some sense? So it's not necessarily the most natural thing in the world. But this kind of thing is very easy for a computer to do, right? If we can somehow codify these production rules and start symbol and terminal symbols, right? It's pretty easy recursively to make a function which says, is this part of my language? And to know if something's a part of your language, you simply need to know if it matches one of these production rules. So if it begins with a 0, you could take this remaining part and say, is this a part of whatever an A is? If it starts with a 0, it might be, is it a 0 followed by something that is a B? And your definition of a B would be something that starts with a 1 and is followed by an A, or something that's just a 1. And you can code this really, really simply. And it's just a bunch of recursive functions that are basically calling sometimes themselves, sometimes other functions corresponding to these different symbols. So this is easy for a computer to do, to analyze something and tell you whether or not it's valid in your language. And this is one way that we do things like parsing languages. So you can make a whole C compiler if you want using this idea. All right, well, that's the analysis part. So the other side of this is synthesis. If you know what the language is, can you come up with a set of production rules, symbols, terminals, and a start symbol? Can you define a grammar? So synthesis. So suppose we know that the language should consist of the following: the empty string, 0, 1, 0, 0, 1, 1, 3 zeros followed by 3 ones, 4 zeros followed by 4 ones, and so on. In other words, our language should consist of words that contain n zeros followed by n ones, where n might be 0, 1, 2, 3, or any other positive integer. And we could abbreviate this as 0 to the n, 1 to the n, where n is bigger than or equal to 0. And this is just saying repeat this symbol n times. So it could be 0 zeros followed by 0 ones. That's our empty string. 1 0 followed by 1 ones, that's this. 2 zeros followed by 2 ones, that's this, and so on. So this is a shorthand way that we could represent this language. And so our question is, can we come up with vocabulary, terminal, start symbol, and productions to give us this language? So any ideas? And at this stage, there's no algorithm for this that we've talked about. This is pure trial and error.
So we could define the starting value that is, right?
Mm-hmm.
Starting value should be A.
Okay.
So it has to start with a 0, right?
Okay.
A could either lead to maybe 0A or 0B. So I'm thinking this way, we would have a, oh, but then how would we, yeah, because then we wouldn't have a way to make just as many zeros as ones. I have an idea.
Okay.
What if we, well, let's just keep the starting symbol as A again.
Okay.
What if we say, from there, you can make 0, A, 1.
So from A,
Oh, that's a good idea.
go to 0A1. I like that.
Yeah, and so I like A either leads to 0A1 or 0, 1. And so that way you can either close it or continue it.
All right, so this will get us to 0, 1 directly. It will also get us to 0, 0, 1, 1, which will also get us to 0, 0, 0, 1, 1, 1. Cool, I like that. That's awesome. What about the empty string?
Okay, change that then. I don't have A go to 0, 1. It could, but you don't want two rules that do the same thing. Have just A go to nothing.
Yeah. So we could add that in, right? A goes to lambda, but if we do that, we can actually get rid of that. Because this gets us the empty string, 0, empty string 1 gets us 0, 1, and so on. So those two rules will actually get you exactly what you want. And terminal symbols are 0, 1, and your vocabulary is 0, 1, and A.
The terminal symbol is the one it has to end on, right?
It's the things that have to comprise your final string.
Oh.
It doesn't have to end with it, but your string can only be made up of things from here. So 0A1 is not a part of our language because it's not composed of terminal symbols, right? So this is perfect. Nice job. So that is a phrase structure grammar that will give us this exact language. And that's how you do these. It's trial and error, right? Try something and it kind of works, but there's a problem with it, so try something different and so on and so forth. Okay, so we'll start tomorrow. We'll do some more synthesis on different phrase structure grammars, and then we'll change gears and look at different ways to represent syntax of a language. Something called Bacchus-Naur form is what we'll do next. All right, cool. I will see you next time.